Hello, Professor. My name is Farzana Bony. Welcome to the presentation for CS512, the Advanced Operating System. My project paper name is Fast File System Checker. Going to the next slide. Here is my outline of my presentation. I will discuss on these topics in my presentation. Going to the next slide. Now I will explain the abstract prompt from this paper. In this paper, the abstract represents a modified fast file system checkers and the modified REST-3 file system that can be integrated with it. The traditional file system checker can identify and recover lost images, but these traditional checkers are very slow and sometimes it is not feasible to work with the modern computational due to the slow speed. The author addressed some challenges like cache failure, hardware error, and file system bug, which is contribute to the slow operation of the file system checkers. In response to these issues, the author proposed a solution, the modified REST file system. REST is designed to outperform to the traditional ext file system for handling random reads and large writes. It provides a more efficient approach to handling cache failure, hardware error. The abstract also illustrates its capability by comparing it with the original file system, where it shows superior performance in almost all scenarios. The proposed fast file system checkers and REST file system offer a promising solution. This checkers is fast enough to keep pace with the growing demand and at the same time can provide support to the existing file system. The key focus is to enhance the performance of file system checks and maintain the data integrity. Now I'm going to the next slide. Now I will explain introduction. Ensuring data integrity is crucial for both personal user and companies due to the high cost and data loss. The file system is like a central component for storing and organizing the data and require careful consideration to maintain the reliability. The various factors like unclean shutdown, bugs, memory corruption, and disk issues can corrupt the file system and leading to significant data loss. Different techniques including copy on write and soft updates are used, but they cannot protect against all faults. Addressing these challenges, the proposed file system introduces the REST file system, emphasizing the fast handling of inconsistency and improve input-output performance. REST enhance the metadata density while the fast file system checker scan the file system significantly faster and maintain the speed even with this aging file system. Surprisingly, the REST file system provides a solution for the efficient data management. Now I'm going to the next slide. Now I will talk about the motivation. Offline file system checkers remain a last resort, restoring the file system image to a consistent state. However, user and administrator are often reluctant to run them due to slow performance, unpredictable downtime, and unreliable progress indications. Addressing these challenges, the author proposed a fast file system checker that performs disk order scan, compress in-memory metadata, and utilize bitmap snapshot. Measurement indicates that it scans the file system significantly faster than the traditional checker. Now I'm going to the next slide. The main purpose of the study is discuss the importance of offline file checkers and introduce a modified file checker system. Although there have been taken many attempts to prevent the data loss and the disk failure by introducing various modifications in online file checker, but some issues are still exist in the file system. So an offline file checker becomes the only savior. The author are hoping to establish the REST file system and the fast checker file system to ensure the data integrity and file uses. In general, file system checker are very slow and cause frustration among the system administrator. But the proposed file system comes as a solution that works with the REST file system to bring a unique experience for faster file checking. Now I will talk about the key definition. The author did not provide any new definition throughout the paper. However, they discussed different keywords in the paper. The first keyword is the superblock. It refers to the collection of metadata that can be related to the properties of an operating system. The next keyword is group descriptor. It refers to the container that holds the block bitmap. It is usually found in each block group so that the data is not lost in terms of the system failure. The next keyword is inode. It refers to an index node that is unique identifier to a specific metadata residing in a file system. The next keyword, the indirect region. It contains the file, indirect block and directory data blocks. This indirect block is usually reserved right after the inode table in the each block. This region is a fast attempted by the fast checker file system for allocating the metadata. The next keyword is cost check. It refers to a file checking technique that does not need all the information stored in an object. After finishing the self-check, it performs the cross-checking by removing all the metadata information. The last keyword is dual FS. It is an operating system that requires a lot of manual prefetching operations that allocate metadata and data individually. Now I'm going to the next slide. Now I will talk about the relative work from the papers. Many researchers have worked on this topic, but I will discuss some of them now. The first work, the mechanism like copy on write, soft updates and back pointer based consistency can handle the file system inconsistency caused by system crash but cannot rectify the error arising from the file system bugs and hardware failure. The next work, the file system bug can be detected and fixed by bug finding tools which can significantly reduce the probability of the file system inconsistency resulting from the coding error. But these tools have not been able to remove all bugs from the file system. The next work, the hardware error can be identified by checksum and corrected with redundant copies. Though this mechanism protects the file system from a wide range of disk faults, but they cannot handle the error coming from the file system source code or the hardware failure that can happen before applying a checksum or creating a copy. The next work, the extent-based file systems such as ext4. The XFS offer a straightforward improvement over the direct mapping of block pointer. The extent can significantly compress the metadata and reducing the amount that the checker has to scan if the average file size is larger and the most blocks are allocated. Next work. Both chunks and Solaris UFS provide an alternative method for addressing checking time. Try to reduce it by dividing the file system into isolated chunks. However, it is difficult to create entirely separate chunks that can be checked independently. It becomes challenging to reliably determine whether a partial check has successfully identified all errors within the system. Now I am going to the next slide. Abhishek Rai uses meta-clustering patch to reduce the amount of time that the fast file system spends seeking between metadata and data by grouping indirect blocks together on disks. Rai achieved this by intelligently grouping indirect blocks together on disks, a strategy that closely aligns with our approach in REST-free file system, and it offers only a partial solution. The next work, the recon protects the file system metadata from the buggy file system operation by verifying metadata consistency. Doing so allows recon to detect the metadata corruption before committing it to disks, preventing its propagation. However, recon does not perform a global scan and cannot protect against error resulting from hardware failures. The next work, it proposes avoiding downtime during the file checking by running the checker as a background process. It does not improve the overall time required to run the checker, but some data may remain offline for long period. It also requires the underlying file system to support soft updates which may not be available. The next work, XQCK takes an different approach to improving the file system checker, focusing on reliability and correctness instead of execution time. It transforms the complicated rules used by the most checkers into SQL, benefiting from the simplicity and compactness of a query language. However, its simplicity comes at some cost. It executes more slowly than the traditional checkers. Overall, all the researchers try to improve the reliability of the file system and protect the user from the potential data loss resulting from the system crashes, system bugs, and the hardware failure. Now I'm going to the next slide. Now I will talk about file system checker background. Usually the file system checker scan all the file system metadata and uses redundant structural information to perform consistency check. If an inconsistency is detected during the scanning process, the checker will repair it with the best effort. E2 file system checker executed its checking rules in 5 phases. The phase 1, scan and check all the inode and indirect block. If the blocks are multiply, claim and rescan all previously checked metadata to choose an owner. The second phase, individually check each directory. The third phase, check the directory connectivity. The fourth phase, check the inode reference count and remove orphan inodes. The fifth phase, update the block and inode bitmaps if necessary. Now I'm going to the next slide. Now I will describe how the E2 file system checker uses this field to verify the consistency of each type of metadata. Once the previous 5 phases are complete, the following rules will have been validated. The first rule, the super block. The second rule, group descriptor. The third rule, directory. The fourth rule, inode. The fifth rule, indirect block. Going to the next slide. Now I will talk about the file system design trade-off. The author observed two file system design decisions that lead to the E2 file system checker's poor performance. The first one, ext file system uses the same allocation strategies for the data block and indirect blocks and storing them in a continuous fashion to facilitate sequential access. The second one, ext file system relies on a tree structure to locate all of the indirect block, imposing a strict ordering of access when checking a file. It prevents the checker from optimizing its access using disk locality. Now I'm going to the next slide. Now I will describe the design and implementation of both REST-free file system and the fast file system checker. These file systems are based on ext and E2 file system checker and reduce the time required to fully check the file system. They each contain some modification designed to reduce the time required to fully check the file system. REST file system improves the metadata density by co-locating all the indirect block in a block group and uses a backpointer based structure for indirect block to better support a fast checker. The fast file system checker uses this modified layout to perform a disk order scan that accesses all the metadata at once and reduces the number of seek operations significantly. The fast checker file system employs a bitmap snapshot to reduce the number of inode and indirect blocks. Now I'm going to the next slide. Now I talk about the goals. There have three goals. The first one, fast scan speed. The second one, robust performance despite file system aging. The third one, competitive file system performance. Now I'm going to the next slide. Now I will talk about REST-free file system. REST-free file system is developed based on ext. REST-free file system inherits most of the mechanism of ext, but except for the two things, the disk layout and indirect block structure. REST-free file system reduces the time spent of file checking. REST-free file system decouples the allocation of indirect block and the data block by reserving a block region. This region store all dynamically allocated metadata, specifically indirect block and directory data blocks. REST file system uses backpointer based data structure, especially the beginning of each indirect block will contain its inode number and the level in the indirect tree structure. REST file system remove the p-allocation mechanism for the indirect block. In this figure we can see ext and REST disk layer comparison. Now I'm going to the next slide. Now I will talk about the fast file system checker. It features three components. The first one, it performs disk order scan to fetch all the metadata into the memory. The second one, it compresses the metadata intensely, remove the memory pressure. The third one, it employs bitmap snapshot that allow it to avoid a costly double inode scan. Now I'm going to the next slide. Now I will explain the disk order scan. The fast file system checker loads all the metadata into the memory in a single sequential scan. Each metadata block is fetched in an order. This file system needs to know the location of each metadata item. It can scan the file system to maximum efficiency. Its execution time varies with the total number of block groups. The file system administrator can accurately and easily evaluate the total time checking time beforehand. Now I'm going to the next slide. Now I will explain the self-check and cross-check rule. Self-checks are performed when the block is fetched into the memory. The self-check of an inode includes the checking, the inode type, the link count, and the allocation state, and the self-check. The cross-check between each inode and its indirect block has two stages. For the fast cross-check, the fast file system checker links together block from the same file using the back pointer to avoid the indirect tree structure. The second cross check verifies the file size. Now I'm going to the next slide. Figure 1. The file size verification. We can see that the logical tree structure used to verify a file size. The bold arrow, they indicate the path followed to retrieve and construct the final out offset. The figure 2. Checksum of each indirect layer. We can see that how the fast checker file system calculates and verifies the checksum of each layer in the tree of indirect blocks. Now I'm going to the next slide. Now I will explain the compression. By using a careful grouping of checking rules, we no longer need to retain all the fields of a metadata item in memory after self-checking it. By compressing the metadata, it lowers the memory consumption. In this figure, we can see the memory cost analysis. This graph compared the memory cost of inode and indirect block before and after compression. Now I'm going to the next slide. Now I will explain bitmap snapshot. The fast file system checker uses a list of bitmap snapshots, each of which shows which data block were allocated by a specific group of inodes. In this figure we can see bitmap snapshot 1 marks block 0, 3 and 4 in use. Bitmap snapshot 2 marks block 1 and 5 in use. When bitmap snapshot 3 marks block 2 and 5, it detects that block 5 has already its use bit set, indicating that it has already been allocated. Now I'm going to the next slide. Now I will talk about the detailed overview of its operation. The first one, the disk order scan. It scans the disks in ascending address order. Read the inode in each block group and self-check them. Read the portion of the data bitmap corresponding to the indirect region. Mark the appropriate bitmap snapshot for each data block allocated. The second one, the cross-check. It's perform a cross-check using the data saved in memory. Verify the total number of blocks. Verify the file size. Verify that the checksum in each layer agree. The third one, correctly doubly allocated blocks. It scans the conflicting inode group. Chooses to which inode to assign the block. This phase do not require much time to execute. Now I'm going to the next slide. Now I will talk about the evaluation. The author evaluate the prototype in three aspects. They compare the performance, they compare the correctness, they measure the two file system relative performance. Now I'm going to the next slide. The first one, checker performance. To measure the performance of E2 file system checker and the fast file system checker, we analyze the time duration to run on different file system images while varying the size and ages. The second one, checker correctness. How the fast file system checker perform in most expensive error case. We test the performance of both checkers. The third one, the file system performance. REST file system performs better in handling random reads and large writes than ext in most cases, but it does not perform so well for handling small reads. Now I'm going to the next slide. Now I will talk about the finding or outcome from this paper. The result of this research shows good performance improvement for the fast file checker system and the REST file system. REST file system performs better for the larger file size. REST file system outperform ext3 by big margin when it comes to handling random reads and the large writes. The author also found that REST file system can compete with ext3 and sometimes can do even better. There is only drawback for REST file system to handle the small size files. Now I'm going to the next slide. Now I will talk about the stains and limitation from this paper. Stains. The first stains is the performance improvement. The second one, the speed improvement while being integrated with the REST file system. The third one, impressive speed to the file checking process. The limitation. The major limitation from this paper is the fast file system solely depend on the data bitmap. The proposed checksum is very simple and may miss data error due to the collision. The third one, it may degrade the performance of the checker process. The fourth one, memory consumption. The last one, this file system is more applicable to the block-based file system. Now I'm going to the next slide. Now I will discuss the future work from this paper. The future research direction will depend on the development of a powerful decoupled file system checker. If the file system can be developed as a standalone program that is detached from the main system, the issue of multiple mistakes in each could be avoided. How the fast file system checker performs with other file system integration. More concentrated research is needed. The small file size performance of REST file system might be improved more. So more research effort is needed on this point. Now I'm going to the next slide. Now I will talk about the conclusion. The traditional checkers are very slow and due to your slow speed it is not possible to work with them. Addressing this issue, the author proposed the modified fast file system checker and REST file system. This file system performs better in most cases. This file system handles the random reads and large writes very well, but this file system performs slightly bad to handle the small reads. More research work and improvement are needed on this file checker system. This innovation results in major improvement to the file checking process. During its operation, it managed to read metadata and operate 10 times faster. Furthermore, it no longer suffers from the file system aging, allowing better prediction of time to completion. That's all of my presentation. Thank you.